How are we doing on it? We have 9 participants. Okay, so okay. Okay, so I'll start with the beginning of the last time. We started last Monday going into the next part of our course, which is really a lot about the electrics of information processing. In other words, using inductors and capacitors and resistors as circuit elements that allow us to do some processing. And the fundamental see, I need to, here we go. The fundamental equation that we will start with, and we'll really use a heck of a lot, is this V equals IR, which is Ohm's law, and just on its face, it describes the loss of electric energy, electric information into a resistor. So the resistor is a sink. It heats things up. It heats up in response to the collision of the currents that flow through, the current that flows through there. But really the most important thing right off the bat that we did was we generalized this equation so that we were able to talk about an impedance. And one of the things that we noted, or maybe we should note, is that the impedance for a resistor is a real number. The impedance for a capacitor and an inductor are complex numbers. So three fundamental components that we're going to consider, and these are actually effects. These are, there's always going to be a resistor, there's always going to be a capacitor, there's always going to be an inductor floating around in our circuit. So sometimes if you're building a circuit, you talk about parasitics, or you're building a device that has a flow that is working with the electrics and the magnetics of the situation, and you'll throw in parasitic resistances, capacitances, and inductance so that you can best design and best understand that those situations, those effects. So again, always associate resistance with a loss. Always associate a capacitance with a storage of potential energy. Always associated inductance with a flowing current, and therefore a kinetic energy. So we derived the impedance of a capacitor, and we derived it from this law here. And one thing that I didn't do, but maybe I'll do this at the risk of confusing you. Sorry about that. One thing that at the risk of confusing you is we had the fundamental law is Q is equal to CV. So the capacitance is defined as the storage of charge and the voltage that charge produces, and then the energy. If you want to think about it this way, make the units work out right and the geometries work out right. That's all the geometry and all the units and the materials are described by the C. And so then if you take the derivative of both sides, d by dt of both sides, if C is a constant, then you get this, this our starting point. And what we did was we substituted in a complex exponential for the voltage and the current, looking frequency component by frequency component, and we derived the generalized impedance, the complex impedance of the capacitor. V over I is equal to 1 over j omega c. So 1 over j omega c plays the role of a resistance in the circuits. And we also derived from a similar equation, we derived the complex impedance for an inductor, V over I rather was equal to L times j omega. So interestingly, that 1 over j omega c was for the capacitor. So omega was in the denominator for a capacitor. For an inductor, it's in the numerator. And so the functional dependence in terms of omega are strikingly different for the capacitor versus the inductor. So the resistance becomes bigger, or the impedance becomes bigger for an inductor for high frequencies, whereas for high frequencies with a capacitor, they don't even see, high frequencies don't even really see the capacitor very much. And we can look at two limits. For example, for capacitance, zero frequency or DC, and that leads to an open circuit, no connection whatsoever for DC. And then for high frequencies, you approach a short circuit for your capacitance. We did an example of that. This was a complicated example where we used superposition. We had a voltage that had a DC part to it, zero frequency part to it, and an AC part to it. Here's a rough sketch of what that is before we go into a capacitor. The DC gets blocked, so this piece here gets taken away. It doesn't make it through the capacitance. And so the only thing that survives is the AC piece of it. And so here's the output. And this when we use the capacitor this way, it's called a blocking capacitor or a blocking cap. And it's a way of taking away the DC component. And so there's a lot of times when you have a sensitive piece of instrumentation and you don't want to subject it to the big sledgehammer of a DC offset. And so you block it, you AC couple. And those are terms of art that describe the use of a capacitor in series. And I say them partly so that you've heard them before in the future, but also partly so that you get an idea that people use these things. This is fairly fundamental and fairly core. So that's our review. And so now we'll pick up where we left off, and we'll talk a little bit more about the inductor. And the inductor has a complex impedance, and the j omega is now in the numerator of this. And so again, two limits. At omega equals 0, I have j times 0 times L, and this is a short circuit. At omega going to infinity, I have J times the infinity times L, and this is an open circuit. So the idea is you connect your inductances, you connect your capacitances in such a way that you route your signals on the basis of their frequency. And the basis of their frequency is filtering. You can use these frequency dependent the frequency independent impedances to sort one frequency from another frequency. And that is hugely important when you're trying to figure out, when you're trying to do information processing. If you're tuned into exactly one frequency at the exclusion of all else, you've drastically reduced your noise or your crosstalk. Let me give you another example, a non-rigorous example of using these inductors and capacitors. And supposing I've got a device, and what I want to do is I want to give this device a DC offset and an AC signal. In other words, supposing I want to bias my device. So I want to be able to put together both a DC battery and an AC signal. So I know I want a DC source, and I know I want an AC source. So I have a battery and I have a function generator, or a battery and an oscillator. And I want to combine them both together and bring them both, and bring both of these into the device at the same time. But supposing in addition to that, the AC will mess up the DC source and the DC can mess up the AC source. In other words, maybe the voltage is so big from my DC source that it'll damage the input of my AC source. How do I do that? Well, I can use an inductor there, and I can use a capacitor there. And so at first blush, what will happen is for the AC signal, this will be like a short circuit. So the AC will get fine, will be happily get to the device. And remember, J omega L for this guy here the impedance of this guy here will be 0 for the DC. So the DC will happily flow into there. So far so good. I've gotten both my DC offset and my AC into the device. And then something very clever happens. This DC gets blocked by that component, because 1 over J0 times C is infinity. So the DC piece doesn't see the AC. And similarly, the AC piece gets blocked by the inductor. And so this is a clever way to bias a device, and this is called a bias T. And again, that's a component that you can build, and it's reasonably popular, and it illustrates a nice application for the use of these complex impedances, capacitors and inductors. Okay, so now to put in a few more rules of the road. Three rules. V equals I times Z. And that's a generalization on Ohm's law. Z can be R 1 over J omega C or J omega L. And then two rules, two other rules. One is Kirchhoff's voltage law. And this says that the sum of the voltages around a loop must close on each other, on itself, or must be zero. So if I start at an elevation and I make a hike up and down some mountains, up and down some hills, but I come back to where I started from, I know I have to be at the same elevation. If I start in a circuit and I started a particular voltage, and I walk around all the elements, all the increases and decreases of voltages, and I get back to the starting point, I have to be at exactly the same voltage. And then the second law, which really is a law, is Kirchhoff current law. And this is the sum of the currents in and out of a node or a spot on the circuit, any particular point on the circuit must equal zero. And this is a consequence of conservation of charge. So we can't create or destroy current. So whenever you see a conservation law, that's absolutely fundamental. It turns out that the laws of physics, philosophically and in practice, all stem from conservation laws. So the very, very highest level of dictum for physics are conservation laws. And so Kirchhoff's current law is related to is directly a consequence of conservation of charge. Charge will neither get created or destroyed. Now you'll notice that I'm putting quotes around the law in Kirchhoff's voltage law, and so Samir is asking a good question. He says, why wouldn't conservation of charge be directly part of conservation of the energy law in physics? There is conservation of energy, there's conservation of momentum, there's conservation of angular momentum, and charge, it turns out, Samir, is a different property of certain particles. of certain particles, protons, for example, and electrons, for example. And so we can keep track of that new property charge separately than energy, or in addition to energy. And so so you're right, energy and charge can be related, but charge is a fundamental property of certain particles, not neutrons, remember, but protons and electrons, and then similarly subatomic particles as well, or even ions. And so charge is just a property that's in addition to energy. That's a great question. So I'm being kind of formal and rigorous when I put these little quotes around the law. It's only a law at low frequencies. Kirchhoff's voltage law is a law only in the sense that you're doing circuit. I'm sorry, yeah, circuit theory, the approximation of circuits. If you're doing full-fledged electromagnetics, there's an additional term that can slip in and change the voltage. So that's something that is probably too clever by half to share with you, but I don't want you to. I don't want to hoodwink you. Let me give you an example, just so that you may have seen. I don't know. Maybe my examples are getting older and older, and less in touch.
I was just wondering, where you wrote circuit theory, what does that, what were you referring to when you said that, so that I can just make my notes clear?
Yep. Circuit theory is the same as low frequency analysis of electromagnetics. So Lauren, when all of you guys go off and take your electromagnetics course, the full equations will reduce down to the circuit theory equations in the limit of the frequency going to 0.
Okay, so would that apply to the Kirchhoff's voltage and current law then? Or?
Kirchhoff's current law always holds, because it's fundamentally related to this conservation of charge. Kirchhoff's voltage law only holds at low frequencies. And let me give you an example of that. If you go back, and some of you may have seen an old television set or an old radio, and it has a little loop of wire coming out of the back of it. And this is what this is a loop antenna. And so what happens is the electromagnetics flows back and forth through the loop, and the loop acts like a net, and there is a voltage induced between these two leads that's proportional to the high frequency fields. There's an additional term to Kirchhoff's voltage law that can be exploited and used in circuits, in electrical engineering. Lauren, let me also explain this circuit theory in one other way for you. And that is, supposing I have a piece of metal or a wire, and supposing I tell you that at this instant here, I have volts equal to 12 volts. at this point of the wire here? Well, if the wire conducts perfectly, V equals IR, there's no resistance down this very, very nice metal wire. So this voltage here should also be equal to 12 volts. And that's true in circuit theory. That in circuit theory, the charge equilibrates fully on the metal surfaces. But we know that it takes some amount of time for that to happen. We know that because the speed of light is finite. So it's going to take about a nanosecond for that charge to move on that, to equilibrate for every foot of wire. So if we take that into account, then the voltage here, if I add a step function to that step here, the voltage will, at this point here, will rise to 12 volts a little bit later than 0. So we're not worrying about that at all when we apply Kirchhoff's voltage law. And that's a good thing, because that's a complicated thing and we don't need to worry about it for a large percentage of our circuits. But as a longtime professor of electromagnetics, I have to confuse you a little bit with those quotation marks. So for now, we're going to declare Kirchhoff's voltage law and Kirchhoff's current law. So let's do an example. Let me have a voltage source here. Let me put a couple of resistors in series with this voltage source. I'll label this resistor R1 and this resistor R2. And then in addition, V equals IR will suggest that there's a current that flows through here. And if I look at a node right between my, my two resistors, I'm going to have a current that flows out of R1 and a current that flows into R2, and those are going to be the same. So if I go painstakingly all the way around the circuit, then the current, there's exactly one current, and that current will be the same everywhere in this loop. So now I can apply Kirchhoff's voltage law, which is the sum of the volts will equal 0 around this loop. And I've got three things that affect the voltage. I don't know how fast to go through this material, so I'm going to be looking at comments and hands that might be raised on the Zoom feedback that I have. But there are three pieces of voltages to worry about, three voltages. I have the voltage of the battery. That's this guy here. And then I'm going to have voltage drops. And then I'll be back to this point here, up by V, down by I1, R1, down by I2, R2, and then back to this point here. And then we just saw by Kirchhoff's voltage law, so we saw by voltage by Kirchhoff's current law that I1 equals I2. So V will equal I times R1 plus R2. And this guy here, I can call an R equivalent. Samir's asking me about a minus sign on the I, and Samir's right. I'm being a little sloppy about my notation. I'm using the fact that I know that I have a positive voltage from my battery, and the overall voltage drop from each of my resistors are going to be negative voltage. So Samir's minus sign that he's putting in, I've already put in here and here. Okay, and it's a direction of the current flow that determines whether current is positive or negative. So I'm assuming a flow of current. And Samir is right. It's dangerous to do that, but I'm throwing caution to the wind and taking my chances. So the voltage drop.
And doesn't it need to be a minus sign inside the parentheses with R1 and R2?
So I have the same sign here as here.
Yeah.
So the currents are going to add, the resistors are going to add here and here. And it's just like, the real question is whether or not you want to put a positive sign or a minus sign there. And so I'm calling this the voltage rise is equal to the voltage drop across the resistors. Okay, and I agree that can be a little confusing, but I think it's nicer it's done that way of thinking is done a lot, and it does get you into trouble from time to time. I'm not going to kid you on that. But in this case, what I mean is the voltage drop across the resistors is I times R1 plus R2, and that's equal to the source, the voltage source start. So now what I'm going to do is I'm going to look at I've got an I flowing in here, and I've got an I flowing in here, and I've got an R1 and an R2. And V1, the voltage drop across this resistor, is I times R1. And I also know that the total voltage is going to equal I times R1 plus R2. That's my equivalent resistance. So I can write V1 over V2, I'm sorry, V1 over V is equal to I times R1 over I times R1 plus R2. The I's cancel. So I have V1 is equal to R1 over R1 plus R2, and that's times V. And what I've done is I've made something called a voltage divider. So these two resistors, this resistor is used, the R1 resistor can be used to divide down the voltage. So this is both an example, an illustration of Kirchhoff's voltage law and Kirchhoff's current law, primarily Kirchhoff's voltage law, but it also teaches us a useful configuration of resistors. So let's do the same thing, but with current. The other way I can arrange my two resistors is not in series, but in parallel. So those are two resistors in series, and those same two resistors in parallel. And now I've got some interesting nodes that are I can use Kirchhoff's current law in a little bit more interesting way. So now I've got a current that flows out of the voltage that sees the parallel combination of those resistors. And at this node, the current splits into an I1 and an I2. And my minus sign convention is going to drive Samir crazy again. By conservation of charge, the current that flows in will equal the current that flows out. So this is just a statement of conservation of charge, and it assumes the direction of the current. And again, that assumption can be kind of dangerous, but in this case, it's convenient and it should be pretty clear. So Kirchhoff's voltage law says that it has to hold, the sum of the voltages around any loop have to hold. And here's one loop. So KVL, this voltage will equal I1 times R1. And here's another loop. So I've got conservation of current. I've got two loops, V equals I1 R1 and V equals I2 R2. And then the last thing I want to draw is an R equivalent which can also lead to a Kirchhoff's voltage law. So this V here is the same as this V here, is the same as this V here. So now I'm just going to start putting Can everyone hear me? Have I lost you guys? It's a Zoom question.
No, you're fine.
Good, good. I keep getting little warning messages on various things. Okay. So I have R equivalent is equal to I1 plus I2. That's our Kirchhoff's law. And that's going to equal I1 times R1. Everybody see where that comes from? I've got V R equivalent. I know my I is I1 plus I2. I know this voltage is the same as this voltage. So I'm setting I1 plus I2 times R equivalent is equal to I1 R1. Now the math is going to be a little bit weird. So I'm going to divide by I1. This quantity I1 plus I2 over I is dimensionless. So I've got resistance equal to resistance. I have 1 plus I2 over I1 times R equivalent is equal to R1. If I go back to here, I have I1 R1 is equal to I2 R2. Or I2 over I1 is equal to R1 over R2. So now I can take this guy here and substitute into there. Now I've eliminated all my current and all my voltage. And the thing I care about is what my equivalent parallel connection of resistors are. So I can solve for that. Multiply through by 1. And my R equivalent is equal to R1 R2 over R1 plus R2. And those are resistors in parallel. So you might have seen that formula before, perhaps in a high school physics course, and so we've approached it, we've derived it from Kirchhoff's voltage law and Kirchhoff's current law for a simple circuit. And that is a good place to stop. I will see you guys on Wednesday when we have our test, our midterm exam. I will email you the midterm exam before the start of class, and then afterwards you'll do your work. You'll PDF and send back the PDF after class. And I'm going to have some buffer time before and after. I'm going to write my exam to be 50 minutes long, but I'm going to have some buffer time before and after for technical difficulties. And then I'm also going to be on Zoom so that you guys can, if you have questions, you can grab a hold of me. So you guys have a great couple of days, and I'll see you on Wednesday.
Thank you.